Imagine this. Billions of years ago, two dead stars engaged in a catastrophic collision, unleashing an explosion so powerful that it rippled across all of space-time. This event not only illuminated a corner of the universe, but also forged some of the most valuable elements we know: gold, silver, and uranium. These elements, formed in the crucible of this ancient cosmic clash, eventually became part of our planet, shaping the very foundation of the world we live in today. This is the story of neutron stars and their kilonova collision, a phenomenon that remains one of the most astonishing cosmic events humanity has ever observed. But what exactly is a neutron star? A neutron star is the ultra-dense remnant of a massive star that has reached the end of its life. When a star that is 8 to 20 times more massive than the Sun exhausts its nuclear fuel, it collapses under its own gravity, triggering a supernova explosion. While the outer layers of the star are ejected into space, the core becomes so compressed that protons and electrons merge into neutrons. This creates an extraordinarily compact object, roughly the size of a city, with a diameter of about 20 kilometers. However, despite its small size, a neutron star can contain 1.4 to 2 times the mass of the Sun. To put this into perspective, a single teaspoon of neutron star material would weigh as much as 10 million tons. This unimaginable density makes neutron stars one of the most extreme forms of matter in the universe. The physical properties of neutron stars are equally fascinating. Some neutron stars, known as pulsars, rotate at incredible speeds, reaching up to 1,000 revolutions per second. As they spin, they emit beams of electromagnetic radiation, which can be detected from Earth as periodic pulses of light. Additionally, the magnetic fields of neutron stars are billions of times stronger than Earth's, so powerful that they can disrupt and annihilate any matter that dares to come too close. But neutron stars become even more extraordinary when they exist in binary systems, two neutron stars orbiting each other in a cosmic dance that eventually culminates in a collision of epic proportions. This cosmic ballet begins as two neutron stars spiral closer together, losing energy through the emission of gravitational waves. These waves, ripples in space-time, are among the most elusive phenomena predicted by Einstein's general theory of relativity. As the neutron stars draw nearer, their orbital speeds increase dramatically, reaching dizzying velocities. Finally, in a fraction of a second, the stars collide in an event known as a kilonova. The energy released in this explosion is so immense that it can brighten an entire galaxy. In the aftermath, the combined mass of the two stars often collapses into a black hole, a region of space-time with gravity so intense that nothing, not even light, can escape. The importance of this collision extends far beyond its visual spectacle. It holds the key to understanding how heavy elements are formed in the universe. During the kilonova explosion, temperatures soar to billions of degrees Kelvin, creating the perfect environment for a process called rapid neutron capture, or the R process. This is the mechanism responsible for forging elements heavier than iron, including gold, platinum, and uranium. In the R process, atomic nuclei rapidly absorb neutrons, creating new elements. Billions of years later, these elements become part of Earth, playing vital roles in technology, science, and even human culture. Gold in wedding rings, platinum in electronics, and uranium in nuclear power. For the first time, scientists have directly observed elements like strontium and yttrium in the plasma left behind by a kilonova explosion. This groundbreaking discovery provides concrete evidence of how heavy elements are formed, confirming theories that previously existed only in simulations. These observations not only enhance our understanding of astrophysics, but also help refine models of stellar evolution and the chemical enrichment of galaxies. Beyond its scientific significance, the neutron star collision is a phenomenon of profound beauty and insight. In 2017, gravitational wave observatories LIGO and Virgo detected ripples in space-time caused by a neutron star collision, while the Hubble Space Telescope captured the light from the resulting kilonova. For the first time in history, gravitational waves, electromagnetic light, and gamma rays were observed from the same cosmic event, marking the dawn of multi-messenger astronomy. This approach allows scientists to study celestial phenomena using multiple types of signals, providing a more comprehensive understanding of the universe. The implications of this discovery go beyond the realm of astronomy. The gold in your jewelry or the platinum in your smartphone likely originated from a neutron star collision billions of years ago. This realization underscores the profound connection between humanity and the cosmos. Everything we consider valuable on Earth has its roots in the violent and creative processes of the universe. Moreover, the study of neutron stars has practical applications in modern technology. Gravitational waves, for example, could be used to improve GPS systems by providing more accurate measurements of space-time distortions. Additionally, research into the ultra-dense matter of neutron stars could lead to breakthroughs in material science, potentially paving the way for the development of super-strong materials. However, neutron stars remain shrouded in mystery. One of the most pressing questions in astrophysics is how matter behaves under such extreme conditions of density and pressure. This is known as the equation of state, a topic that challenges even the most advanced theories of nuclear physics. Inside a neutron star, matter may exist in exotic states, possibly as quark-gluon plasma or other unknown forms of matter. If confirmed, these discoveries would revolutionize our understanding of the fundamental building blocks of the universe. The neutron star collision is a testament to the universe's power and complexity, but it also serves as a reminder of how much we still have to learn. With each new discovery, we unlock another piece of the cosmic puzzle, bringing us closer to understanding the origins of the universe and our place within it. Who knows what future neutron star collisions might reveal? Perhaps they will offer answers to some of the most profound questions in science, or even inspire the next generation of explorers to venture into the stars.